Continuing on our lecture on enzyme kinetics, we will now discuss the allosteric models in enzyme substrate binding. Now, allosterism comes from the word allostery, which is the indirect interaction between distinct and specific binding sites. So in this case, you have two substrate. Actually, it's not only limited to two substrate. You can have two or more substrate. So those substrates bind to different areas or different sites in the different distinct and specific binding sites to your enzymes. Now, depending on the binding or the effect of that binding of that substrate, it can somehow, or rather not somehow, it can directly or indirectly affect the binding of the next substrate. So it can be an activator, whereas your substrate binds to one site, it increases the binding activity of the enzyme to another site. Or it can be an inhibitor. So one substrate binds to one site and it inhibits or decreases the binding activity. So it decreases the binding activity at another site. So basically, that's your inhibitor. So in this model, it's not, we simplify this in such that we will discuss homotropic allosterism, so simplified model in such that you have only one type of substrate. So that substrate can either act as an inhibitor to your to the other, its own peers, which is other substrates, or it can be an activator to the other substrate. So to simplify this model, homotropic, single substrate only. So there are also models or heterotropic allosteric models in such that you have two different substrates. But for simplicity, as an introduction to allosterism, we'll just discuss about a single type of allosterism, the homotropic. You have only one type of substrate. So our reaction goes like this. So you have your enzyme, so it binds to your substrate. It binds to your enzyme. So you form your enzyme substrate complex. Now we refer this one as C1. Later on, you will see C1. And then it can also bind, the same substrate can also bind to another site, so another complex. So we have two distinct complex because the substrate binds to two different sites on the enzyme. Now, this complex, say complex 2, can you can add another substrate here. So since you have this simple model has two binding sites for the enzyme, so the C2 can accommodate another substrate, so it binds reversibly to form the C3 complex. So you have two substrates binding to a single enzyme, and then that can form catalytic reaction to form the product. And then another look at this one. So your enzyme and substrate complex C1 can form again a catalytic activity. So you have formation of your product with just one binding of the enzyme from the substrate. And this complex 1 can also accommodate the second substrate to form the complex 3. So all in all, you have how many? Four reversible reactions and then 2 irreversible reactions. Those are the catalytic steps. Okay, so you have quite complicated compared to the simple microelement and enzyme substrate enzymatic reactions, but let's make sense of that. Now, unlike the previous video where we use the law of mass action and we modeled the different rates, the concentration rates, the changes in the concentration over time of each species, we will try a different approach this time. Why? Because remember, how many different species do we have? So we have the enzyme, we have the first complex, we have the second complex, we have the third complex. So 3 complexes, 1 enzyme, and then how many times the substrate binds that. So just for a single complex, for example, just getting E, we have 1, 2, and then this is the third, 3 reactions to consider, so it's quite long. And then how many of them? 1, 2, 3, 4, and then we need to consider the product and of course the substrate as well. So that's quite a lot. So let's simplify our life. So let's just create a simple kinetic rate equation. So just to simplify it, the kinetics, using the rate kinetics or kinetic constant equation. So remember the kinetic constant equations, you have your K is equal to products over reactants. Okay, so that's a simple. So we can say KD1. So letting the simplification for the concentrations of each species. So we have E, C1, C2, C3, S, and P for each of the following species. And then let's say KD1. So what is KD1? Where is KD1? KD1 here. KD1 is the product is the enzyme substrate complex, which is complex 1. And your reactants are the enzyme and the S. So we have KD1 is equal to ES over C1. And then rewrite that such that we get C1 here, we get ES over KD1, that's equal to C1. The same goes for KD2 and alpha KD1. So we have C2. We can now interpret, or we can now express our complexes in terms of the concentration of the enzyme and the substrate with our constants K, KD1, KD2. Sorry, this is KD2, and then we have KD1, KD2, and then you have the alpha. Okay, so KD1. So remember, we have 4 equations, 4 reactions here, but if we use alpha KD2, the equation, we only have this equation for the C3 complex. But if you try with this one, you will still end up with this expression for C3. So C3 will end up with this type of equation. Okay, so you now have 3 equations, each of them expressing the complexes in terms of the enzymes and the substrate with your constants KD1, KD2, and alpha. Now, by the way, alpha is this is another constant. So we can say that alpha is your binding, the effects of binding of one substrate to another substrate. So that's why we have an alpha here. Later we will be discussing about that value of alpha. Now, going back. So applying your steady state approximation, we have the formation of the complex is, remember, the ds over dt is, or rather the steady state approximation, dc over dt is approximately equal to 0. So you have your the reversible reactions are at steady state. So we just consider, for the rate of the reactions, consider the catalytic steps. So you have the velocity. So this is a simplified one. So for the velocity, we will just consider the rate of the reaction of the catalytic steps. Those are the irreversible catalysm. So we have K-cut. So where do they come from? So we have 2 rates. Remember, we have 2 irreversible reactions. This one and this one. So the rate of this one, so we can say R1 is equal to K-cut times the ES. This is C1. Remember, C1. And then for the other one, you have the rate 2. We have beta K-cut times C3, complex 3. So that is our rate reaction. So we get the velocity here. So the rate of the reaction, the total reaction is equal to the rate 1 plus rate 2. So K-cut C1 plus K-cut C3. Beta K-cut C3. Whereas beta is as another parameter like alpha. If alpha relates to the effect of the binding of one substrate to another, our beta is the indirect effect, or the beta is the effect, or how we numerically express how one substrate affects the formation of the product of the other substrate. So anyway, we'll go back on that one later, as I told you. Okay, now we have this generalized equation V is equal to K-cut C1 plus beta K-cut C3. Now we have your velocity equation in terms of C1 and C3 variables. So you have 2 variables and the constants K-cut, beta, and K-cut. So basically 2 constants and 2 variables. But we want to simplify everything, so let's just try to express them as a single, the velocity in terms of a single variable. So remember, we managed to express C1 and C3. So we will just substitute them to the equation. So k cat is equal to S over KD1 plus beta k cat equal to ES squared over alpha KD1 KD2. Now, let's further remove one of the reaction, because remember, you still have two variables still. So you have enzyme and the substrate. Now, if you remember, the enzyme, the number of enzymes, it's an enzyme. It doesn't necessarily, it's not consumed nor it's not generated in the reaction. Therefore, the total number of enzyme is a constant. So we can express this variable more in such that we can say that the Vmax is equal to k cat over EO. So this is from the first video lecture. So I'm no longer going to reiterate what I said over there. So anyway, we have this equation from the Vmax equal to k cat over EO, same as before. So we just rewrite this one in terms of k cat. So substitute k cat with Vmax over EO. So you have this reaction. So still we have two variables. We still wasn't able to remove another variable, but we have EO. Remember, EO, the total enzyme concentration, at any time the total enzyme is constant. Therefore, the EO is equal to E, the number of free enzyme, plus the one bound in complex 1, plus the one bound in complex 2, plus the one bound in complex 3. So that's the total enzyme concentration. Now, if we substitute them, we can remove the value of the free enzyme E. So, we just have to substitute this one. So again, your total enzyme is equal to C1 plus C2 plus C3. Substitute this to our equation. So we have your a rather large amount of equation. So EO, again, C1, C2, and C3, we can re-express that as enzyme and substrate. So from here, we just substitute EO, this equation, to the EO. So you have your velocity is equal to Vmax over S. So basically, it looks daunting. I mean, this is less simple than the previous one. But if you look at it closely, you have here only one independent variable rather than two, the enzyme and the substrate variable. So you have here that we can now express our velocity in terms of a single variable, which is the number of substrate. So, and looking at it closely, why do I say that? Because Vmax is a constant, beta is a constant, KD1, KD2 are constants, and then you have the alpha, another constant. So basically, all of them are constants, which can be obtained in the experiment. So we are just left with an equation. We have one independent variable, the V, and one dependent variable, the V, and one independent variable, S. So that's basically that. So why do we have to do that? So we can actually graph them. So the alpha is the cooperativity, and you have your beta for activity. So in here, we have a graph showing the red one, the red colored graph shows us the total velocity, S. And then these are the individual contributions. So the one in green is a contribution from the enzyme substrate, and the one in blue is the one with two substrates bound to the enzyme. So here we just have one substrate bound. So one substrate, these are the two substrates. Okay, and then this is the total. Now, here we just arbitrarily said that KD1, KD2. So let's just arbitrarily put a value there. So let's just say that the binding of the substrate to the two different sites is the same. And let's peg it as an arbitrary value, 5 micromolar. We just want to put an arbitrary value so we can graph it. And so, let's say, remember we have two other parameters or two other constants, alpha and beta. So what is the, let's say, status quo, there is no cooperative binding and there is no change. So the catalytic rate of the product formation for the enzyme that binds two substrate is the same to that of the enzyme that binds only one substrate. So we have here your enzyme substrate beta 1. So as you can see, it's still there's a disparity in the total velocity over the one that has two substrate, the enzyme that binds to substrate in here. So okay, now what about we introduce a positive binding cooperativity. So that means we have alpha is equal to less than 1, because alpha is the rate of dissociation. The KD1 or KD2 is the rate of dissociation. So if you have a small alpha, so that means it increases. The binding of one substrate increases the binding of the next substrate. So you have here, again, we choose an arbitrary value, 5 micromolar, same as the first graph, and then you have less than 1. So let's put it at 0.1. So you have, that means your substrate increases the binding of the next substrate by a factor of 10. So you can see here now that the enzyme substrate complex binding to substrate is very close to the total rate of reaction. So it has a very, very small gap as compared to the reaction of the substrate that only binds one, or rather the enzyme that only binds one substrate. Now, moving on. How about we have your positive, or rather activation. One substrate is an activator of the next substrate. So that means you have a beta value that is greater than 1. So your remember, K-cut is for the catalytic. So the greater K-cut, the faster the reaction, the catalytic reaction you have, or rather the faster the product formation. So that means your substrate is an activator of the other substrate. So you have beta of a positive or greater than 1. So you have 5. So as you can see, much closer, even though there is generally very close to the total reaction time. So for the no activator, it's actually very, very low. So the enzyme substrate complex binding two substrates is very close to the total rate kinetics as compared to this one. But if you look at the shape, for the activity or the binding activity, that this one is steeper. So here you have a steeper curve. So sorry, it's the same color. Wait. So you have here, let's try turquoise. Okay, so in here you have a very sharp incline, so a very steep formation of your maximum, very near to the maximum. But if you look at this one, the rate becomes a bit different. So it has a more subdued, the shape of the curve is more flatter than the other, so less steep, but still you get a rather hyperbolic one. Now, how about negative binding? So the enzyme substrate complex, the binding of one substrate decreases the binding of the next substrate. So you have now a very different graph. So you can see here the blue, this is the S complex going very, very low, in such that the enzyme the one that binds only one substrate reaches higher at greater or at less substrate concentration. And then how about substrate inhibition? So as you can see, the effect is actually very low. So if you have substrate inhibition, this one, the effect is very low, almost very low activity of the enzyme. Okay, so that's that. So for the reference, you can look up at Mathematical Biology and Introduction by Murray, 2007. We have Methods and Models in Mathematical Biology by Johannes Muller, Christina Cutler, and of course, for the graphs, you have your Department of Washington Ed. Okay, so that's it for this lecture.